Hi, today I'm going to be going over heaps. I'm going to give a basic introduction as to what they are, their important methods, and how we're going to represent them in code. And then I'm going to do a couple of practice problems, one of which you may have seen in your section, but that's okay. Um, so what is a heap? Well, a heap is a binary tree for the purpose of this class, and it's going to be one of these two variants. It's either going to be a max heap, where the root item is the largest item that you have, and at each item, its children are going to be smaller than it. So each node is larger than its children. Or it could be a min heap, where the root item, is the smallest item out of everything, and each node is smaller than its children. So its children would be larger than it. Um, and keep in mind that a binary tree is not the same thing as a binary search tree. In a binary search tree, for each item, the left child has to be less than, but the right child has to be greater than. We're not going to be following those properties. The binary search tree is a bit too strict for how we want to implement our heap. So our heap is just a binary tree, which just says that each node has up to two children. So it could have no children, where it's a leaf. It could have one child, or it could have two children. That's all that a binary tree specifies. So let's get some practice with identifying what is a valid binary heap. So we're going to be answering this question for both of these heaps. So this one on the left, we want it to be a max heap. Well, let's see if that's true. The top item seems to be the largest item out of everything we have, which is good. Is 17 larger than 15? Yes, it is. Is 17 larger than 11? Yes, it is. And then we move down to the next level, because remember, this is a property that has to be applied recursively. So you have to check the 15. Is it larger than both of its children? It is. And the 11, is it larger than, well, it only has one child, but is it larger than it? It is. And we can see that this binary tree shape is almost filled out. It's pretty much as filled out as it could be since there's no node here, which means that the shape is also good. So this is a valid max heap. Now this one on the right, the shape looks a little weird, but it is actually correct in terms of how filled out it can be, because the first level is full, the second level is full, and the next level has one item put at the right slot. So that part's good. But we want it to be a min heap. So we check, is 3 less than 8? It is. Is 3 less than 12? It is. Is 8 less than 6? It is not. So if this were a valid min heap, you would have to have these two be swapped or something. But the way it is right now, this is not a valid min heap. So hopefully that makes a little bit more sense than me just explaining by words what a binary heap looks like. And hopefully you can use this to figure out for yourself what a binary heap should look like. So let's go over some important heap operations. The first is insert. So the algorithm to insert something into a heap is you first just put it, without thinking, just put it at the first available slot. So you would look at the last layer and you would look at the first open slot in the last layer. Or if that last layer is full, you would put it in the next layer. So you would just put it at the first available slot, which would be here, the left child of 14. And then if there's any problems with where that, like what that number is, and if it breaks the heap properties, then you just swap it up, percolate up as we call it, as necessary. So if we wanted to call insert of, as we can see, this is a max heap. So if we wanted to call insert of 30, how would we do that? Well, like I said, just first without thinking, just put it where it has to go. So put the 30 there, and then we want to percolate it up. So we look up. So the parent of 30 is 14, and we want this to be a max heap. So since 14 and 30, that breaks that max heap property, we have to swap these. So then this goes to looking like this: 18, 16, 30, 11, 3, 14. And again, this applies recursively, so we're not done yet. We want to look up another layer, and the 30 is larger than the 18, which means we have to do another swap. And then That leaves us with 30, 16, 18 after these two swapped, 11, 3, and these 11 and 3, 16, those didn't get changed at all. And now we have it like this, which is now a valid max heap. So that's good. Insert's pretty simple. Now remove min or remove max, this depends on what kind of heap you have. If it's a min heap, it'll be remove min, and if it's a max heap, it'll be remove max. But in both cases, it works pretty much the same. So the first step is you just want to remove the item that's at the root. So you save that because you want to return it. So you save it, and then you just take it out. And what do you put in its place? You put the last item in your tree in its place. So you would look at the last layer and the rightmost item of the last layer. And you just, again, without thinking, you just put that at where the root is. And then, as you need to, in case it causes problems with the heap properties, you just swap it down, percolate it down this time. So again, it's not too complicated. You just need to remember to do things in the right order. So how would we do that here? As we can see, this is a min heap, so we're going to be doing remove min. So what do? We want to store this 3, so we just take it out, and we have 3. That's what we're just going to return later. And then we just replace it with this 50, because that's the last item in our binary heap, because it's in the last layer, and it's the only item in the last layer. So we take this out, and we replace the 3 with 50. So then it looks like 50, I was going to get a little cramped here, 8, 13, 18, sorry for my handwriting, and then 40. And then now we have to do some swaps to make sure everything works, because 50 is not the smallest item in our min heap. So now we have to swap down. So it's not the same as swapping up. You have to look at 2 children if it has 2 children, and then you have to make a decision. So 50, its children are 4 and 8, and 4 and 8 are both smaller than 50. So which one do we swap it with? Well, since this is a min heap, we want to swap it with the smallest of our 2 options. We'll find that that's what works, because if you swap the 50 with the 8's now at the root, but the 8 isn't our smallest item in the whole heap. But if we swap 50 with 4, 4 is now at the root, and that makes sense because that is what should be at the root. It's our new minimum. So we swap the 50 with the 4 since that's the smaller of the 2 children. So just trust that that works. So we get we get 4, and then 50 went here, 8, 13, 18, 35, 40, and then we have to do one more swap down. Again, you want to swap it with the smaller of the 2 children in the case that both are smaller than the current item, which is true. So you look at 50's children, you have 13 and 18. 13 is the smaller of the children. So let me put it over here. I've managed my space very poorly. 4, and then you have 13, 8, 50, because you swapped 13 with a 50, 18, 35, and 40. And then now this is a valid min heap, and we just have access to this 3. You would have wanted to saved it in a local variable like an int to return, and then you just return this, and you're good. That's all that does. Remove max works pretty much the same way, except when you're swapping and you have 2 children, you swap with the larger of the 2 children if it needs to be swapped, so on and so forth. So both of these algorithms aren't too complicated. They just take some practice to remember exactly what's going on. So how do we want to represent heaps in our code? Well, a really, really simple way to do it is just represent it as an array. And as you'll see with this example, you just pretty much flatten your heap and you put it item by item in your array. So the 1 goes first, and then you look at the next layer, 54, then 3, next is 54, next is 3, and then you just go left to right, 94, 62, 39, 11, and then you do the same thing. You go left to right. So that's all you do. You take the first layer, you input it. You take the second layer, input it left to right. Third layer, input it left to right. And it makes it pretty simple to go from heap to array and from array back to heap. And there's 2 different ways that you can represent it as an array. You could start at index 1, as we've done in this example, Personally, I think that this makes it a little cleaner, so you don't have to mess with index 0. Index 0 would just not be used at all, and the root item would go at index 1, and then that lends itself to this formula where you can go from item to its child, or both of its children, and from item back to its parent with a really, really simple formula. You can try it for yourself if you don't believe me, but for an item, its left child is going to be at 2 times that index, and its right child is going to be at 2 times index plus 1. For example, 94's children are 96 and 95. So index 4 times 2 is 8, which is the 96. 4 times 2 plus 1 is 9, which is the 95. So that's correct. That works. And then to go from index back to its parent, all you need to do is divide by 2. You may be wondering why that works, because you have a plus 1 in one of them. It's because of the way that Java integer division works. If you divide something by something else, it's always going to round down. So if you have 3.2 as your result, it's just going to be 3. So we can test it with a few things. 43 divide 12 by 2 is 6. Is 43's parent 39? It is. 50 divide 13 by 2, you get 6.5, which, as I said, you round down always in Java when you're dividing integers, and that becomes 6 as well, which is right. 50's parent is also 39. So this works, and it's pretty simple to implement. Another way you could do it is starting at 0. There's benefits and drawbacks to doing both of these. It just depends on how you want to do it. It's really up to you as a designer, but you could do it this way. You start at the 0, and then you just do the same thing. You flatten it. You put the 1, then you put the 54 on the 3, then you put the 94, 62, so on. And it makes the formulas a little bit different, but still not too bad. I'm not going to go through exactly why it works or like showing you that it works. Just trust that it works and try to remember this. But it's not too bad. So next we're going to go over this problem called ternary heaps. You may or may not have seen this in the section, but I'm going to go over it anyway. It's pretty much the same as inserting into a binary heap, except the catch is that we're going to have 3 children, or up to 3 children per node, instead of up to 2 children. This is just to show that the properties of a heap are strong and are still going to be applied in a shape like this, and it's kind of to drive home, again, how inserting into a heap works, no matter what the shape is. So a ternary heap, like I said, is going to be up to 3 children per item, so it's going to look like something, and then 3 things, and then 3 things from each one, so on and so forth, and this would have 3, like that. But let's do the algorithm as we know it. So we put the 5 at the first open spot, which is our root spot. So 5 goes here, and then we put the 20 at the first open spot, which is here. Check if we need to percolate it up, which we don't, since 20 is larger than 5. Then we put the 10 at the next spot, which is the middle child, since there's up to 3 children. And no swap needs to happen here since 10 is larger than 5. And then we put the 6 at the rightmost child. And again, 6 is larger than 5, so it can stay there. The next item we put is here, the 7. 7 goes in now the next layer, since the first and the second, or the 0th and the first layer are full. 7 goes here. We realize that 7 is smaller than 20, so they need to swap. So let me do it like this. I'm using OneNote. That's the fastest way to do it. So the 7 goes here, the 20 goes here. Next item we put, now that we've done the 7, is this 3. 3 goes here, and now we clearly see we need to swap the 3 with the 7, since 3 is smaller. And then, again, we have to apply swapping recursively. So we look up from 3, and we find that 3 is smaller than 5. Big revelation. You swap the 3 with the 5. Now 5 goes here, and now 3 is our root, which makes sense because 3 is the smallest of all the items we have so far. Next item we're going to put, now that we've done the 3, is the 1. So the 1 becomes the rightmost child. Let me give myself a little bit more space. It's hard to draw ternary heaps. So the 7 goes here, and the 1 now goes here for now. Percolate it up. So we're going to swap the 1 with the 5, and then we're going to swap the 1 with the 3. So 1 and 5 swap. So 5 goes here, and then 1 and 3 will swap. So 1 goes here, 3 goes here. And now 1 is our new minimum, which again makes sense because 1 is the smallest of all the items so far. And then now we move on to 2. This sort of, all the children of 3 are full. So we put the 2 at the leftmost of 10. And we see we're going to have to swap 2 with 10, but we don't need to swap 2 with 1. So we only have to do 1 swap for a change. So we take out the 10 and swap it with the 2. And then if you want, you can do one last check to make sure that all the heap properties apply. 1 is smaller than 3, 2, and 6. 2 is smaller than 10. 3 is smaller than 27 and 5. Everything seems to check out. And the heap is as full as it can be. That's good. That's what it would look like. And then now how do we want to represent this as an array? Well, as we saw with binary heaps, what we just do is we go with the first layer, put the first item, and then we go the next layer, go from left to right, and then the next layer go from left to right. We're going to do the same thing with our ternary heap. Now this problem specifies that we want to start at index 0. Remember I said earlier you can choose whichever one you want, well, unless the problem tells you what to do. In that case, you go with the problem. So we're going to put the 1 first. Oops. So it's 1, and then we saw it's 3, then 2, then 6 as the next layer. And then it's 27, 5, and 10. If we draw this as an array, as we're used to seeing, we start it with index 0. This is 0, 1, 2, and so on. This is what it ends up looking like. So it's pretty similar. It's like the same way as you would represent a binary heap, except just with 3 children. But that means that our formulas are going to be a little different to find child to parent and parent to children. So let's go over how it would be. So going from child to its parent, for a binary heap, remember when we're starting at index 0, this is a formula from going from child to its parent. As we can see, there's a 2 here. So let's try to do some guess and check. What if we just replace the 2 with a 3? Would make sense, right? So let's say that was a horrible arrow. Let's say that it's I minus 1 divided by 3. Does that work? Well, let's check it out. So what is the child of index 7? What's the child of 10? We can see that it's 2. So let's try to do index 7 up to its parent. 7 minus 1 divided by 3 is equal to 6 divided by 3, which is index 2. And index 2's item is our 2. 10's parent is 2. So that works out. That may have been a lucky guess, though. Let's try it with now this 5. So item 5, its parent is this 3. So item 5 is at index 7, or index 6, excuse me. So 6, let's try the formula. 6 minus 1 divided by 3 is equal to 5 over 3. And 5 over 3 is like 1 and 2/3, so it would be 1.66 repeating. But as I said earlier, with Java, when you're dividing integers, you always round down, no matter what. Even if it's 1.9999, you round down. So this becomes 1. So this formula is telling us that 5's parent is the item at index 1. What's the item at index 1? Well, it's the 3. And 5's parent is 3. So that seems to check out. We'll say that works. Now, how do we want to do this? Parent to children. Again, for reference, here's the formula from going to parent to children in a binary heap. And again, we can try to just change this 2 to a 3. Maybe do a lucky guess again. 3i plus 1, 3i plus 2, and I don't know, we have a third child, so why don't we just add a 3i plus 3? That seems to make sense intuitively, right? It's just what you would guess. So let's check that this works. Let me erase all this. So for index 0, its first child would be at 3 times 0 plus 1, Its second child would be at 3 times 0 plus 2, and its third child would be at 3 times 0 plus 3, and that's indices 1, 2, and 3. And the children of 1 are indeed 3, 2, and 6, as we can see from this. So that works for that. Let's try it for, um, let's see, our item 3. So item 3, its children should be 27 and 5. So item 3, 3 times 1 plus 1, 3 times 1 plus 2, 3 times 1 plus 3. This gives us 4, 5, and 6. What are the items at 4, 5, and 6? Well, indeed, it's our 27 and 5. So this fully works. And as you can see, this gives you some practice with sort of applying a formula to a sort of different set of rules. If you want, you could implement a ternary heap like this. It's pretty similar. It's not too bad. So that's how you do that. So the last thing I'm going to go over is Floyd's Buildheap algorithm, which is something you want to use when you have a list of items already given to you and you want to build a heap just from that list. You don't have a stream of data that's just coming in whenever. It's just a predefined set of items and you just want to build a heap from that. Floyd's algorithm is what you want to use because it's doing the job in n time, which is really, really good. Now to do this, first you want to just pretend like your item is a valid binary heap. There's going to be a lot of violations in this list of items if you just draw it as a binary heap, but the first step is just to draw it out and pretend it's a binary heap. So I've done that step for you because that would take me a long time with my drawing pad. So this is how this array looks as a binary heap. Now as you can see, there's a lot of problems with it, but we'll get to that. So that's step 1. Step 2 is to go from the bottom layer up, and at each item, you look at if it has to be percolated down, and you do it if necessary. So you want to start from the bottom, and you want to start from going from right to left. So you're starting with essentially in your array, the very last item, and going left. So let's start that. Draw my arrow here. At this last layer, there's no items here, there's no items here. 32 is our first thing that we come across. Does this need to be percolated down? No, because there's nothing below it, so it doesn't violate any rules on its own. And then we go to the next layer. 6, there's no children. 20, there's no children. 12, no children. 17. Now we want this to be a min heap. Is 17 less than 32? It is, so it can stay where it is. So actually that layer is good. And then we go up to here, 15, and now we see the 15 needs to be swapped with 6. Because the 6 is smaller. So we take out the 15 and replace it with a 6, and we put the 15 where the 6 was. So that's good. And then we go here. 7, does this need to be swapped with anything? No, this is good, this is good, this is good. And then we go to our 10, which is our last layer to look at. And we see if it needs to be percolated down, which it does because both of its children are smaller than it. So we pick the smaller of the children to swap it with, as we do in a percolate down. So that means it's going to swap with a 6. So you got a 6 here and a 10 here. And as you can see, we had to look at every item once, and we only had to do a couple swaps. So essentially, don't worry about the math. You can look up a proof for it if you want, but just trust that this reduces to theta of n time, which is really good. Let's check one last time to make sure that this is a valid min heap. 6, both children are larger. 7, both children are larger. 10, 17, looks to be good. So that's how you use Floyd's Buildheap algorithm. It's not too bad. You just first pretend that it's a valid binary heap, and you start with the last item going backwards, and then you do percolate downs. So that's all I got for today. Thanks for watching.